Say I want to measure exactly how fast a piece of code runs. The first instinct is usually to just grab a stopwatch, but a program running on an old laptop will take far more seconds to finish than the exact same code running on a massive server rack. Time in seconds tells us about the physical hardware, not the code itself. To measure the actual efficiency of an algorithm, we need a universal metric that ignores the hardware entirely. We do that by counting the execution steps, the total number of lines the code actually runs. Look at this for loop. If you count the lines written on the screen, there are only 2, but the computer runs the initialization step once and then executes the inner print statement 4 separate times. So regardless of processor speed, this algorithm always takes exactly 5 steps to complete. This gives us a fixed, standardized way to measure an algorithm's complexity. Now imagine writing an algorithm to sort a list of numbers. The time it takes will change depending on the data we feed it. If the list is already in perfect order, the program barely has to do any work. If it's completely backward, the code is forced to execute the maximum number of steps. There are 3 performance bounds: the best case, omega, the average case, theta, and the hardest scenario, big O. We exclusively design for the worst-case scenario, ensuring the program won't crash under maximum pressure. That's why we focus heavily on big O notation. A modern processor can handle roughly 100 million instructions in a single second. At that massive scale, adding 1 or 2 fixed, unchanging steps to our code has 0 measurable impact on performance. Because of this, when calculating big O, we drop the constants. If our code takes a fixed number of steps, c, plus a variable number of steps, n, we ignore the c. The complexity is simply big O of n. And if a piece of code is entirely fixed, we denote it as big O of 1. The exact number of small fixed operations is just noise. Big O notation only cares about the trajectory of the algorithm, how it scales when the variable input grows. Look at nested loops. This outer loop runs n times, containing an independent inner loop running m times. For every outer iteration, the inner completes its cycle. We are adding m together n times. Multiplying the boundaries gives us big O of n times m. Consider a loop where I squared is less than n. To find its big O notation, simply isolate the variable. Move the square to the right side, transforming it into a square root. The loop runs until I reaches the square root of n. Identifying the correct big O notation always comes down to carefully analyzing the mathematical termination point of the loop. Here is the final challenge. In this block of code, the inner loop's boundary isn't a separate independent variable. It is actually bounded by I, the variable from the outer loop. You might be tempted to say the complexity is n times I, but that cannot be the answer. The variable I is strictly internal. A user only provides n, so our final answer must be defined entirely in terms of n. Let's track the execution step by step. When the outer loop starts, the inner loop runs 1 time. On the next pass, it runs 2 times, then 3 times, and so on. As it advances, it builds a right triangle. Mathematically, this triangle represents exactly half of a perfect square grid. The total number of steps is 1/2 n squared. Apply our rule about dropping constants. The 1/2 fraction is a constant, so we throw it out. The true time complexity is simply big O of n squared. We have covered a lot of ground today. Take a screenshot of this summary. Count steps instead of seconds, ignore all constants, prepare for the worst-case scenario, and multiply the bounds of independent loops. Internalizing these 4 rules gives you the exact foundation you need to break down the advanced algorithmic problems in our upcoming lessons.